In the southern hemisphere, where the Milky Way spills out in its brightest glow, something lurks that is so strange, so terrifying, and simultaneously so beautiful that astronomers still cannot fully explain its nature. This is an object that has already nearly destroyed itself once, ejecting mass equal to 10 of our suns into space. This is a star that shines 5 million times brighter than our sun. This is a time bomb capable of transforming at any moment, in 1,000 years or tomorrow, into one of the most powerful explosions our galaxy has ever witnessed. Its name is Eta Carinae, and today we'll journey to this cosmic monster to understand why scientists from around the world keep their eyes fixed on it, why it has rewritten astrophysics textbooks, and why its fate may be linked to the future of life on Earth. But first, we need to understand exactly where this star is located and how people even learned of its existence. The constellation Carinae is part of what the ancient Greeks called the ship Argo, that legendary vessel on which Jason and the Argonauts set sail for the Golden Fleece. The constellation was so enormous that in the 18th century, French astronomer Nicolas Louis de Lacaille divided it into 3 parts: Carina, the keel; Puppis, the stern; and Vela, the sails. Eta Carinae ended up in the bow of this mythical ship. For inhabitants of the Northern Hemisphere, this star is practically inaccessible. It sits too low above the horizon, and for most, never rises above the horizon line at all. But for those living south of the equator, Eta Carinae is one of the brightest objects in the night sky. At least, that's how it was in the mid-19th century. The first records of this star date to 1677, when English astronomer Edmund Halley, the same one for whom the famous comet is named, observed the southern sky from the island of St. Helena. He cataloged the star as a 4th magnitude object. Nothing special, an ordinary star among thousands of others. But by the 1730s, something began to change. The star grew brighter, then brighter still. By 1782, it had reached 2nd magnitude and became one of the notable stars of the constellation. Astronomers of that era recorded these changes but didn't attach particular significance to them. Variable stars were known, and brightness fluctuations didn't seem extraordinary. Everything changed in 1837. That year, Eta Carinae began rapidly gaining brightness. It grew brighter and brighter, as if someone were slowly turning up the dial on a celestial searchlight. By 1843, the unthinkable occurred. The star became the 2nd brightest in the entire night sky, yielding only to Sirius. But Sirius lies just 8 light years from us. Eta Carinae, 7,500 light years away. This meant its true luminosity was simply monstrous. This event entered astronomical history as the Great Eruption, and it lasted not an instant, not a day, not a week. It continued for nearly 20 years. For 20 years, the star blazed with a brightness that seemed impossible according to all the physics of that time. What happened? To understand this, we need to figure out what Eta Carinae actually is. And here's where it gets interesting. Eta Carinae is not one star. It's a binary system consisting of 2 massive stars orbiting each other in a highly elongated elliptical path. The primary star, which astronomers call Eta Carinae A, is a BlueHypergiant with a mass of approximately 100 to 150 solar masses. Its companion, Eta Carinae B, is smaller but still enormous, from 30 to 80 solar masses. But wait, 150 solar masses? Is that even possible? For a long time, it was thought not. There existed the so-called Eddington limit, a theoretical boundary for stellar mass above which radiation pressure from within should tear the star apart. This limit was estimated at roughly 120 to 150 solar masses. Eta Carinae balances right on this boundary and possibly even exceeds it. And here lies the first mystery. How can a star with such mass even exist? Why hasn't it blown itself to pieces? The answer is that it constantly loses mass. Eta Carinae is literally evaporating into space. Its stellar wind, the stream of charged particles that all stars emit, is so powerful that each year it loses mass equal to roughly 1,000th of the sun's mass. This might seem like little, but over 1 million years, that's already 1,000 solar masses. And such stars live only a few million years. It's as if a person were losing a kilogram of weight every day. You can't last long like that. But even this constant stellar wind doesn't explain what happened during the Great Eruption. Then, Eta Carinae ejected 10 to 40 solar masses of material into space, and did so not gradually, but over just a few decades. This was a catastrophic ejection that created one of the most beautiful and mysterious structures in the entire universe, the Homunculus Nebula. If you've ever seen photographs of Eta Carinae taken by the Hubble Space Telescope, you've surely noticed the two enormous orange-red lobes resembling an hourglass or a little human figure, hence the name Homunculus. This structure is a direct consequence of the Great Eruption. The ejected material is expanding at about 600 kilometers per second and has already reached nearly a light year in size. A light year, that's the distance light travels in 1 year. About 10 trillion kilometers. And all this space is filled with gas and dust ejected from the depths of a dying star. But why does the ejection have such a strange shape? Why two lobes rather than a sphere? Here we approach one of the most intriguing mysteries of Eta Carinae, the role of its companion star. Eta Carinae b orbits the primary star with a period of about 5.5 years. But this orbit isn't circular, it's highly elongated. At the closest point, which astronomers call periastron, the two stars approach so closely that the distance between them is only about 1.5 astronomical units, less than the distance from a sun to Mars. At the farthest point, a pastron, they separate to 30 astronomical units, roughly corresponding to Neptune's orbit. Every 5.5 years, when the stars approach each other, something dramatic occurs. The powerful stellar wind from both stars collides, creating shock waves with temperatures of tens of millions of degrees. These collisions generate powerful X-ray radiation that astronomers detect with space telescopes. But the strangest thing happens directly during periastron. For approximately 3 months, the system's X-ray emission virtually disappears. Astronomers call this the X-ray minimum or spectroscopic event. The last such event occurred in 2020. The next is expected in 2025. What causes this eclipse? The most probable version is that during the approach, the companion plunges into the dense stellar wind of the primary star, which absorbs the X-ray radiation from the shock wave. But the details of this process remain subjects of debate. Let's return to the shape of the Homunculus Nebula. Why is it bipolar? One hypothesis connects this precisely to the binary nature of the system. During the Great Eruption, interaction between the two stars may have directed the ejection primarily along the poles of the system's rotation, creating the characteristic hourglass shape. An equatorial disk of denser material impeded ejection in that direction, and matter rushed where resistance was less toward the poles. But there are more exotic versions too. Some researchers suggest that the system once contained not 2, but 3 stars. And the Great Eruption was the result of a catastrophic merger of 2 of them, while the third, the current companion, remained in its orbit. This would explain both the colossal energy of ejection and its strange shape. But whatever the true cause, the result is evident. Eta Carinae is surrounded by an expanding cloud of its own material, and this cloud continues to yield surprises. In 2005, astronomers discovered another, much more ancient structure around the homunculus, the so-called outer ejecta. These are traces of a previous ejection that occurred about 1,000 years ago. And beyond that, even fainter traces of ejections stretching back thousands of years. This means the Great Eruption of the 19th century wasn't a unique event. Eta Carinae has experienced similar catastrophes repeatedly. It seems to pulse, periodically shedding shells and building up tension again. Why does this happen? To answer this question, we need to peer into the very heart of the star and understand what processes occur there. Eta Carinae is in a late stage of its evolution. Despite being probably only a few million years old, an infant by stellar standards, it has already consumed a significant portion of its nuclear fuel. Massive stars live fast and die young. The greater a star's mass, the faster it burns hydrogen in its core and the shorter its life. Our sun will shine stably for another 5 billion years. Eta Carinae, at its mass, will live only a few million years total. And most of that time is already behind it. When a star exhausts hydrogen in its core, it begins burning helium, a product of hydrogen fusion. When helium runs out, carbon, then oxygen, neon, silicon. Each successive stage proceeds faster and faster. If the hydrogen stage takes millions of years, the silicon stage lasts only a few days. At the end of this chain, an iron core forms. And here comes the end, because nuclear fusion of iron doesn't release energy. It absorbs it. The star's core loses the pressure source that kept it from gravitational collapse. And catastrophe strikes. In fractions of a second, the core implodes. The star's outer layers crash inward at tens of thousands of kilometers per second. They bounce off the compressed core and rush back outward. The star explodes. This is called a supernova. But in Eta Carinae's case, everything could be even more dramatic. At masses exceeding 140 solar masses, the explosion can be so powerful that the star leaves behind neither a neutron star nor a black hole. It is completely destroyed. Such events are called parent stability supernovae. They occur when photons in the core of a supermassive star become so energetic that they begin converting into electron-positron pairs. This reduces pressure inside the star and triggers catastrophic collapse. An alternative scenario is a hypernova, an explosion accompanied by narrow relativistic jets and the most powerful gamma-ray burst. In any case, when Eta Carinae explodes, it will be a spectacle humanity will never forget. How bright will this explosion be? By various estimates, apparent brightness could reach -7 to -10 magnitude. For comparison, the full moon has a brightness of about -12. This means Eta Carinae will be visible even in daylight. It will become the brightest supernova in the history of observational astronomy. But there's bad news too. If the explosion is accompanied by a gamma-ray burst, and if one of the jets is directed toward Earth, the consequences could be catastrophic. Gamma radiation can destroy the atmosphere's ozone layer, leaving the planet defenseless against solar ultraviolet. This would lead to mass extinction comparable to the greatest catastrophes in the history of life on Earth. Sounds frightening? Don't rush to build a bunker. Fortunately, the rotation axis of the Eta Carinae system is oriented at approximately 45 degrees to the line connecting it to Earth. This means that even if the explosion produces jets, they will most likely miss us. We'll see a spectacular light show, but the deadly radiation won't touch us. Most likely. The problem is we can't be absolutely certain of this. The system's rotation axis could change as a result of interaction between the stars, or our calculations could contain errors, or hypernova physics could yield surprises. And one more unpleasant detail: we don't know exactly when this will happen. Astronomers say the explosion could occur at any moment within the next million years. This sounds comforting until you realize that any moment includes tomorrow, and next week, and next year. Moreover, given the distance of 7,500 light years, light from the explosion will reach us 7,500 years after it occurs. This means Eta Carinae could have exploded back in the time of the ancient Sumerians, and we simply haven't received that information yet. Every night, when residents of the southern hemisphere look at the constellation Carina, they see light that left the system 7,500 years ago. They see the past and the present. Possibly a spectacular explosion has already happened, and light from it is racing toward us through the cosmic void at 300,000 kilometers per second. But let's leave apocalyptic scenarios and return to what we can study here and now. Eta Carinae isn't just an object for observation. It's a unique laboratory for studying the most extreme processes in the universe. Using its example, scientists test theories of stellar evolution, investigate mass loss mechanisms, study interactions in binary systems, and try to understand what happens to stars at the limit of their possible existence. And every year it yields new surprises. In 2019, a group of researchers published results of many years of observations showing something unexpected. Eta Carinae is getting brighter. After the Great Eruption of the mid-19th century, the star gradually dimmed, hiding behind dust clouds it had created itself. By the early 20th century, it was barely visible to the naked eye. But in recent decades, the trend has reversed. From 1998 to 2019, Eta Carinae's brightness increased almost tenfold. And this isn't a fluctuation, it's a steady trend. The star seems to be emerging from shadow. What does this mean? One version is that the dust surrounding the star is gradually dispersing, allowing us to see more direct light. Another is that the star itself is experiencing another period of activity. Perhaps we're observing preparation for a new eruption. Data from the Hubble Space Telescope show that the structure of the Homunculus Nebula is changing right before our eyes. Bright points flash and fade. Filaments expand and collide. It's like watching slow-motion footage of an explosion, except the explosion happened 180 years ago, and we're observing its consequences in real time. The central region of the nebula is particularly interesting, where the star itself hides. For a long time, it was practically inaccessible to observations in the optical range due to the dense dust veil. But infrared telescopes and interferometers have allowed us to peer through this shroud. What astronomers saw turned out to be more complex than expected. Around the primary star, a complex structure of gas flows and shock waves was discovered. Eta Carinae's stellar wind collides with the companion stellar wind, creating a turbulent zone with temperatures of tens of millions of degrees. This collision produces X-ray radiation detected by orbital observatories. But most amazingly, the scale of this interaction changes with orbital period. Every 5.5 years, when the stars approach, the entire system experiences a crisis. X-ray emission first intensifies, then sharply drops. Spectral lines in the optical range undergo dramatic changes. Something happens inside this fiery hell, but exactly what remains unclear. In 2020, another stellar approach occurred, the 12th since the discovery of periodicity in 1997. And for the first time in history, it was observed with the full arsenal of modern instruments. The Hubble and Chandra space telescopes, ground-based interferometers, radio telescopes, and optical spectrographs around the world. Results are still being analyzed, but preliminary data have already shown something interesting. The system isn't behaving quite as models predicted. The X-ray minimum arrived earlier than expected. Some spectral lines changed unpredictably. Perhaps the companion star penetrated deeper into the primary star's atmosphere than in previous approaches. Or the stellar wind structure changed. Eta Carinae continues to surprise. But let's step back from technical details and consider more global questions. Why is this star so important for astronomy? What can it tell us about the universe as a whole? The thing is, objects like Eta Carinae are cosmic rarities. In our galaxy, which contains several hundred billion stars, objects of this class can be counted on one hand. BlueHypergiants with masses over 100 solar masses are exceptional phenomena. And BlueHypergiants in binary systems experiencing catastrophic eruptions. That's an absolutely unique case. Studying Eta Carinae, we gain invaluable information about how the most massive stars in the universe form and evolve. And these stars play a critical role in cosmic ecology. Massive stars are factories for heavy elements. In their depths, thermonuclear fusion occurs that transforms hydrogen into helium, helium into carbon, carbon into oxygen, and so on through the periodic table up to iron. And during the supernova explosion, even heavier elements are created: gold, platinum, uranium. Every oxygen atom you breathe was created in the depths of a massive star billions of years ago. Every calcium atom in your bones, every iron atom in your blood, all of it is stellar ash, ejected into space during supernova explosions. We are literally made of stars. And when Eta Carinae finally explodes, it will scatter a new portion of heavy elements across space. In millions of years, this material will become part of gas and dust cloud from which new stars and planets will be born. Perhaps on one of those planets, life will someday arise. And the living beings that appear there will be partly composed of atoms that once belonged to Eta Carinae. This is an amazing thought. A star now, blazing 7,500 light years from us, will someday become part of something new. The death of one star is always the birth of something else. But massive stars affect their surroundings not only through their death. Even during life, they are the most powerful energy sources shaping the structure of the interstellar medium. Eta Carinae sits at the very heart of a vast star-forming region known as the Carinae Nebula. This is one of the largest active stellar nurseries in our galaxy. Here, among swirls of gas and dust, thousands of new stars are forming, from small red dwarfs to new giants. And Eta Carinae exerts colossal influence on this process. Its ultraviolet radiation ionizes surrounding gas, creating the characteristic reddish glow of the nebula. Its stellar wind sweeps away material, forming cavities and bubbles. Its previous ejections created shock waves that compress gas and trigger the formation of new stars. Eta Carinae is simultaneously destroyer and creator. It annihilates gas clouds around it while triggering the birth of new luminaries. The Carinae Nebula is a place of astonishing beauty. If you could transport yourself there by spaceship, a picture would open before you that's impossible to describe in words. Colossal pillars of gas and dust, lit from within by young hot stars. Bright arcs of shock waves, dark globules, dense cocoons inside which new suns are forming. And at the center of all this magnificence, the blindingly bright point of Eta Carinae, surrounded by the ghostly glow of the homunculus. This is a sight worth any journey. Unfortunately, a journey to Eta Carinae is impossible for us. Even at light speed, the trip would take 7,500 years. On our current spacecraft, hundreds of millions of years. But we have telescopes. Over recent decades, our capabilities for observing Eta Carinae have radically expanded. The Hubble Space Telescope allowed us to see the finest details of the homunculus structure. The Chandra X-ray Observatory captured radiation from stellar wind collisions. The Spitzer and Herschel infrared telescopes showed dust distribution around the system. Ground-based interferometers allowed us to resolve details in the central region inaccessible to ordinary telescopes. And this is just the beginning. In coming years, new instruments will enter service that will transform our understanding of Eta Carinae. The JamesWebb Space Telescope, with its unprecedented sensitivity in the infrared range, will allow us to peer through the dust veil directly to the star's surface. The extremely large telescope in Chile, with a mere 39 meters in diameter, will be able to distinguish details a few astronomical units across at the distance to Eta Carinae. We're entering a golden age of research on this amazing system. But you know what's most interesting? Despite all our telescopes and computer models, Eta Carinae continues to pose questions we cannot answer. Why did the Great Eruption occur? Yes, we know the star ejected enormous mass of material. But what exactly triggered this process? Was it the result of internal instability? Or collision with a companion? Or merger with a third star? Models give different answers, and none of them explains all the observed facts. What is the exact mass of each star? This might seem like a simple question, but the answer remains ambiguous. Estimates of the primary star's mass vary from 100 to 150 solar masses, a spread of 50%. For the companion, uncertainty is even greater. What is the true mechanism of the periodic X-ray minima? We've been observing this phenomenon for a quarter century, but its physical nature is still debated. And the main question, when and how will it die? Will it explode as an ordinary supernova? Or as a hypernova with a gamma-ray burst? Or as a parent stability supernova, leaving nothing behind? Or, also possible, will it collapse directly into a black hole without a bright flash? We don't know. And this not knowing is part of what makes Eta Carinae so captivating. Science isn't a collection of ready answers. It's a process of constant investigation, constant wonder, constant collision with the unknown. And Eta Carinae is one of the brightest examples of how much in the universe remains beyond our understanding. But let's digress from technicalities and think about the more global picture. Why is this star important for humanity? What can it tell us about ourselves? For ancient peoples of the Southern Hemisphere, Australian Aboriginals, New Zealand Maori, South African tribes. The constellation Carinae was part of the night landscape long before Europeans first raised their telescopes to it. Each culture had its own myths and legends connected to these stars. Interestingly, in some southern sky traditions, mentions of variable stars have been preserved, objects that change brightness over a human lifetime. Perhaps among them were memories of previous Eta Carinae eruptions, those whose traces we now see as the outer shells of the nebula. European astronomers first paid serious attention to it in the early 19th century. John Herschel, son of the famous William Herschel who discovered Uranus, spent several years in South Africa cataloging stars and nebulae of the southern sky. He observed the beginning of the Great Eruption and left detailed records of the star's brightness changes. By 1843, when Eta Carinae reached its peak brightness, it became a sensation among astronomers worldwide. No one could explain how a star at that distance could shine so brightly. The physics of the time simply didn't allow such a possibility. This was one of those moments in science history when nature shows us how incomplete our theories are. After 1843, brightness began to fall. The star gradually dimmed, hiding behind an expanding dust cloud. By the 1870s, it had dropped below naked eye visibility. It seemed the show was over, but astronomers didn't forget about it. Throughout the 20th century, Eta Carinae remained an object of close observation. With each new instrument, from photographic plates to CCD arrays, from ground-based telescopes to space observatories, we learn more about it. In 1968, the first infrared image was obtained, showing that the star is surrounded by an extensive cloud of warm dust. In the 1990s, the Hubble Space Telescope took the famous images of the homunculus that became this object's calling card. In 1997, periodicity in spectroscopic changes was discovered, leading to understanding of the system's binary nature. Each decade brought new discoveries, and there's no reason to believe this process will stop. Now, in the 21st century, we stand on the threshold of a new era in studying Eta Carinae. New telescopes, new analysis methods, new computer models. All this allows us to ask questions that previously seemed impossible. For example, can we predict the explosion? Theoretically, possibly. Several years or even months before core collapse. Changes should occur in the star that will be reflected in its appearance. Increased luminosity, spectral changes, intensified stellar wind. If we watch Eta Carinae closely enough, we might notice these precursors, but we might not notice them. Our models might prove incomplete, or the star might behave unexpectedly. That's precisely why it's so important to continue observations. In 2019, an international group of astronomers launched a project for continuous monitoring of Eta Carinae using a network of telescopes around the world. The goal is to miss no change, however insignificant it might seem, because any change could be the first sign that the star is entering the final stage of its life. And if we see these signs, we'll have time to prepare. Direct all telescopes at that point in the sky. Record every detail. Become witnesses to one of the most spectacular events in astronomical history. This will be a moment that enters textbooks for millennia to come. But even if the explosion doesn't occur in our lifetime, and given astronomical timescales, that's quite probable, studying Eta Carinae will remain an important and exciting endeavor, because this star is a window into extreme physics. It's an opportunity to see processes normally hidden from us in inaccessible depths of space. It's a chance to test our theories at the limit of their applicability. And finally, it's simply beautiful. There's a special beauty in objects that exist at the edge of possibility, in systems balancing between life and death, in phenomena that challenge our understanding. Eta Carinae is one such phenomenon. It reminds us that the universe is far stranger, more complex, and more astonishing than we could imagine sitting on our small planet around an ordinary yellow star on the outskirts of an ordinary spiral galaxy. But this ordinary planet gave rise to beings who learned to look at stars, who built telescopes and spacecraft, who created physics and mathematics to understand what they see. And someday, descendants of these beings may perhaps travel to other stars. Maybe they'll find worlds born from Eta Carinae's ashes. Maybe they'll meet other life there, life that also consists of stellar matter, that also looks at the sky and asks questions. That's a distant future, but it begins here and now, with every glance at the night sky, with every question about what's up there. Eta Carinae will wait. It blazed long before the first human raised eyes to the stars. It will blaze for a long time yet, maybe thousands of years, maybe millions, or it'll explode tomorrow. We don't know. And that not knowing is precisely what makes it so compelling. Now let's discuss some details that often escape attention in popular accounts of this star. Let's start with a question that might seem simple. What color is Eta Carinae? The answer is more complex than it appears. The star itself, or rather, both stars, is bluish-white. This is the typical color for hot, massive stars with surface temperatures of tens of thousands of kelvins. But we virtually never see the star directly. What we see is light reflected and re-emitted by surrounding dust and gas. And dust changes color. It absorbs blue light more strongly than red, so the star appears redder to us than it actually is. This phenomenon is called interstellar reddening, and in Eta Carinae's case, it's especially strong due to the dense environment. As a result, in photographs, the homunculus appears orange-red, though the star inside, it is blindingly blue. Another interesting question: why does the Homunculus Nebula have such a clear bipolar structure? We've already discussed the possible influence of the second star and the equatorial disk, but there are subtler details. If you look closely at high-resolution images, you'll notice that inside each of the two large lobes are even smaller structures: arcs, filaments, knots. These structures probably arose from non-uniformity in the original ejection. Material didn't fly out in a smooth stream, but in series of pulses. Each pulse created its own shell, and now these shells overlap, creating a complex layered picture. Moreover, the expansion velocity of different parts of the nebula differs. Material at the poles moves faster than material closer to the equator. This creates a kind of stretching effect. The lobes become increasingly elongated over time. It's also interesting that the nebula isn't symmetric. The southeastern lobe differs slightly from the northwestern one in shape and brightness. This may indicate asymmetry in the original ejection, possibly related to the companion star's influence or non-uniformity in the stellar wind. Another mystery is the so-called little homunculus. This is a smaller structure located inside the large homunculus, oriented roughly perpendicular to its axis. It was discovered in 2003 and still lacks a satisfactory explanation. Perhaps these are traces of some local ejections unrelated to the Great Eruption. Perhaps they formed as a result of interaction with the companion star. Perhaps it's an optical illusion caused by peculiarities of light reflection in the dust. We don't know. This is another item on the long list of unsolved questions. Let's talk about how the distance to Eta Carinae is measured. 7,500 light years. This estimate migrates from article to article. But where did it come from? And how reliable is it? Measuring distances in astronomy is an entire art. For nearby stars, the parallax method is used, measuring the tiny shift in a star's position against the sky caused by Earth's motion around the sun. But at distances of thousands of light years, parallax is too small to measure even with the most precise instruments. For Eta Carinae, a different method was used, measuring the expansion rate of the Homunculus Nebula. We know the nebula's angular size from observations. We know how much time has passed since the Great Eruption. If we measure the expansion velocity through Doppler shift of spectral lines, we can calculate how far away the object must be for the angular size to match the linear size. This method is called the expanding nebula method, and it gave an estimate of about 7,500 light years. But there are nuances. Expansion velocity isn't the same in different parts of the nebula. The nebula's shape isn't a perfect sphere. Orientation relative to the line of sight isn't known with high precision. All these factors introduce uncertainty into the distance estimate. Recent measurements using the Gaia Space Telescope, a specialized observatory for measuring stellar parallaxes, gave a somewhat different value. By some estimates, Eta Carinae may be somewhat closer, about 6,500 light years. The difference might seem insignificant, but it affects estimates of luminosity and mass. If the star is closer, it's less bright and less massive than we thought. This could change our understanding of its evolutionary status and how soon it will explode. Discussions about distance continue. This is another example of how, in astronomy, even basic parameters can remain subjects of debate. Now, let's talk about temperature. The surface temperature of the primary star is estimated at roughly 15 to 20,000 kelvins. For comparison, the sun's surface temperature is about 6,000 kelvins. Eta Carinae is 2 to 3 times hotter. But this is the photosphere temperature, the star's visible surface. Inside, the temperature is much higher. In the core, where thermonuclear reactions occur, temperature reaches hundreds of millions of degrees. And in the zone where stellar winds from the two components collide, temperature rises to tens of millions of kelvins. That's enough for the gas to emit X-ray radiation. X-ray observations are one of the key tools for studying interaction in this binary system. It was precisely changes in X-ray flux that allowed establishing the orbital period and understanding the geometry of stellar wind collision. Interestingly, during the X-ray minimum, when the stars are closest together, radiation doesn't just weaken, it virtually disappears. This indicates that the shock wave zone becomes completely immersed in dense material that absorbs all X-ray radiation. The details of this process are still being modeled and discussed, but the general picture is clear. Every 5.5 years, the system experiences a dramatic interaction episode whose consequences we record with our instruments. Let's return to the question of mass. Why is Eta Carinae's mass so important? Because mass determines a star's fate. Stars with masses less than 8 solar masses end their lives relatively peacefully. They shed their outer shells and become white dwarfs. This is our sun's future. Stars with masses from 8 to roughly 25 solar masses explode as Type II supernovae and leave behind neutron stars, tiny superdense objects city-sized but with the sun's mass. Stars with masses from 25 to roughly 40 solar masses also explode as supernovae but leave behind black holes. But what happens to stars with masses over 100 solar masses? That's already the realm of theoretical speculation, because such stars are very few and none of them has yet exploded before our eyes. Eta Carinae falls precisely in this range. Its fate is terra incognita for astrophysics. According to one model, a star of such mass should experience a parent stability explosion. This happens when photons in the core become so energetic that they begin converting into electron-positron pairs. This reduces pressure, the core contracts, thermonuclear reactions sharply accelerate, and the star either completely tears itself apart or sheds a significant portion of mass and continues to exist until the next instability episode. The Great Eruption may be precisely such an episode. Not the final explosion, but an intermediate flash, a harbinger of the coming catastrophe. According to another model, Eta Carinae may collapse directly into a black hole without a bright flash, without an explosion, simply quietly disappearing from the observable universe. Such events are called failed supernovae, and they may occur more often than we thought. Which scenario plays out, we'll learn only when it happens, or when someone builds a model precise enough to predict the outcome. But for now, models give different answers. And this isn't a flaw in science. It's a sign that we're at the cutting edge of knowledge, where certainty hasn't yet been achieved. Let's discuss observational prospects. The next approach of the system's components is expected in 2025. It should occur around mid-year. This will be the 13th period of periastron observation since the discovery of periodicity. Astronomers are preparing for this event in advance. Observation programs are being developed, telescope time is being allocated, joint campaigns using multiple instruments are being planned. The goal is to obtain maximally complete data on what happens during the approach. How does X-ray emission change? How does the spectrum transform? Are there changes in nebula structure? Each new observation period provides additional data that allows refining models and better understanding the system's physics. And who knows, perhaps this time we'll see something completely unexpected. Maybe the star will finally decide to give us a real surprise. Though, honestly, the real surprise would be the explosion, and that we most likely won't see in the foreseeable future. But in astronomy, you can never be sure. Let's return to the question of how dangerous Eta Carinae is to Earth. We've already said that if the explosion produces a gamma-ray burst directed our way, consequences could be catastrophic. But how likely is such a scenario? Let's start with the fact that not all supernovae produce gamma-ray bursts. According to current understanding, gamma-ray bursts are associated with the formation of rapidly rotating black holes in the cores of collapsing stars. This requires special conditions: high core mass, rapid rotation, a certain chemical composition. Eta Carinae is a good candidate for these conditions, but it's far from certain everything will come together just right. The star may have lost too much angular momentum through its massive stellar wind, or the core might not be massive enough, or something completely different might happen. A parent stability explosion, for example, which doesn't produce a gamma-ray burst. Even if a gamma-ray burst occurs, the jets aren't necessarily directed our way. We've already said the system's rotation axis is oriented at a significant angle to the line toward Earth. This reduces the probability of a hit. But let's look at the problem from another angle. How close would a gamma-ray burst need to be for its consequences to be catastrophic? By various estimates, the critical distance is from several hundred to several thousand light years. Eta Carinae sits right at the edge of this range, 7,500 light years. This means that even if a jet is aimed directly at us, consequences might not be as terrible as often described in popular articles. Yes, the ozone layer would suffer. Yes, there would be increased ultraviolet. But this might not lead to mass extinction, rather to ecological stress that the biosphere could handle. Of course, these are speculations. We've never observed a gamma ray burst at such distance and don't know exactly what the consequences would be. But there's definitely no reason to panic. Moreover, the probability of this happening in our lifetime is extremely small. Even if Eta Carinae explodes within the next 1,000 years, already an optimistic estimate, the probability of it happening in the next 100 years is about 10%. And that's assuming the explosion is inevitable within the next millennium, which is also not certain. So yes, Eta Carinae is a cosmic time bomb, but time is the key word. By human standards, it's very significantly delayed. This doesn't mean we shouldn't study it. On the contrary, the more we know, the better we're prepared for any scenario. But there's definitely no need to fear it. Let's talk about something more pleasant about beauty. Eta Carinae is one of the most photogenic objects in the universe. Images of the Homunculus Nebula gracebook covers, posters, science website backgrounds. But what makes it so beautiful? First, color. Orange-red glow against black space creates dramatic contrast. This isn't accidental. Color is determined by dust temperature and light scattering characteristics. But our brains perceive it as something aesthetically appealing, warm, and majestic. Second, shape. The bipolar structure with two symmetric lobes creates a sense of order amid chaos. It's like a butterfly or an hourglass. Recognizable patterns our brains love to find in the surrounding world. Third, detail. At high resolution, fine filaments, knots, arcs are visible in the nebula. Complex internal structure you could examine endlessly, finding ever new elements. And finally, story. Knowing that this beauty was born from catastrophe, that it's the result of a stellar explosion, that inside hides a dying luminary. All this adds depth and significance to the aesthetic impression. The beauty of space isn't just visual pleasure. It's the beauty of understanding. When we look at a photograph of Eta Carinae and know that before us is evidence of colossal physical processes occurring at scales our minds can barely comprehend, then beauty becomes something more. This is the beauty of knowledge, the beauty of science. And this is perhaps the most important lesson Eta Carinae can teach us. The universe isn't obligated to be beautiful. It isn't obligated to be comprehensible. It isn't obligated to meet our expectations and hopes. But it is beautiful, comprehensible, and astonishing. Not because someone made it so, but because we learn to see and understand. Every time an astronomer points a telescope at a distant object, they perform an act of meaning creation. They transform meaningless photons into knowledge. They connect themselves to the universe. And Eta Carinae is one of those threads that connect us. It will burn for many more years or explode tomorrow. It will surprise us or turn out duller than we thought. It will be beautiful because we've learned to see beauty. And it will remind us of who we are, beings who look at stars and ask questions. This began millions of years ago, when our distant ancestors first raised their eyes to the night sky and wondered, "What's up there?" And it continues to this day when we aim space telescopes at a small point in the constellation Carina. Eta Carinae is a question we're still seeking the answer to. And perhaps in this search lies the meaning of what we do.